Welcome to another class. In this lecture, I will briefly discuss about the compact heat exchangers and the extended surfaces heat exchanger, and then I will talk about briefly regarding the design steps and the design equations and the correlations of the compact heat exchangers, and I will try to explain about few graphical representation regarding the design of the compact heat exchanger, and then at the end I will come up with a design problem in which we will try to evaluate the heat transfer coefficient as well as the pressure drop correlations for a particular geometry. Let's have a look on the introduction. First of all, the compact heat exchangers of plate fin and the tube fin types, that the tube bundles with very small diameters, and they are sometimes called the regenerative type, that has many applications in the gas flows. So regarding the geometry or the size, so a compact heat exchanger having a surface area with the area density greater than about 700 meters square per meter cube, that is the surface density, and it is quite arbitrarily referred as the compact heat exchanger. So this is just a rule of thumb that the area density, if is in this range, that will be considered as the compact heat exchanger. The heat transfer area is usually increased by the incorporation of fins on the external surfaces. So that's why most of the times the tubes, I have already explained that in the shell and tube heat exchangers. So when we have the gas flow on the shell side in the shell and tube heat exchanger, so the heat transfer coefficient is very small. So in order to increase or enhance the heat transfer coefficient, we install the external surfaces, or known as fins, on the outer side of the tubes in the shell and tube heat exchanger in order to increase the heat transfer coefficient. The heat transfer surface area is increased by the fins to increase the surface area per unit volume of the exchanger. The device is referred to as the micro heat exchanger if the surface area of the density is above 10,000 meters square per meter cube. The compact heat exchangers have wide applications in the industry, especially for the gas to gas and gas to liquid heat exchangers. But some examples includes the vehicular heat exchangers and condensers and evaporators in the air conditioning and the refrigeration industry, aircraft oil coolers and automobile radiators and air coolers. There are numerous applications of these compact heat exchangers. So why we prefer this kind of heat exchanger? Because they occupy very less space and they have very high surface area. So that's why we can use this kind of heat exchanger for many applications, even for the space applications, because of the limited size and the extended or the higher surface area for the heat exchange. Compact heat exchanger are also used in the cryogenic processes, electronics, and these are few examples which is basically which represents the applications of the compact heat exchangers. So talking about the heat transfer matrices for the compact heat exchanger, as you can see on the left hand side of this slide, that here we have the internal flows inside the tubes, and the circular fins are actually installed on the outer side of the tubes that actually increase the surface area. So increasing the surface area actually increase the heat transfer rate. So this is known as the fin tube or the circular tubes or the circular fins. So on the other hand, we have the plate fins, right? So this is simply known as the cross flow, right? So the one flow is from right to left, and and the second flow is inward. So the flow, both the flows are at 90 degrees. So we have different plates, right? The first plate, the second plate, and the third plate, and in between the plates we have the corrugated surfaces, right? Corrugated surfaces, so in different directions. So let's say this corrugated plate has different dimensions or different direction, and this corrugated plate has different direction. So that's why this is called the plate fins or the single pass kind of geometry. Here we have some different kind of geometries, like we have the flat tubes which are fixed with the different continuous plate fins, and it actually increases the surface area. And similarly, in this geometry, instead of having the flat plates, we have the circular tubes. So there are always two kinds of flows. The one is maybe the cold fluid, and the second is the hot fluid. So the cold fluid is passing through these tubes, and the hot fluid is moving in this direction. So there is no direct contact between the two fluids. So either would be the case that the hot fluid is either moving inside the tubes or the cold fluid is moving inside the tubes. In most of the cases, the cold fluid is moving or the hot fluid is moving inside the tubes, right? So one of the best example is, you can see in the real life that the fins are actually installed on the engine of the motorbike. You can easily see that there are small fins or the extended surfaces on the engine of the motorbike. So this is one of the best example of the extended surfaces heat exchanger. So the heat transfer and the pressure drop characteristics have been studied experimentally by the Case and London. There are some figures that has been developed that can be used to determine the Colburn factor, J factor, using the Reynolds number. So here this expression is very important, that the Colburn factor J is a function of the Stanton number and the Prandtl number with the power of 2 by 3. So this is very important expression that you have to use it for further design of the compact heat exchanger, and from this expression we will be able to develop the new expression that can be used to find out the heat transfer coefficient, right? So here we have already studied about the Prandtl number, right? So the Prandtl number is the multiplication of the viscosity multiplied by the heat capacity divided by the thermal conductivity. So here the new number is that is known as Stanton number, and Stanton number is the combination of three different numbers, right? The Nusselt number, the Reynolds number, and the Prandtl number. So we have already seen all the dimensionless numbers, so we will just put their values or their expression into this form, and after simplifying that we will have the easiest or the smallest expression for the Stanton number, which is the ratio of the heat transfer coefficient divided by the mass velocity or the mass flux multiplied by the heat capacity. And we also know that the Reynolds number either can be expressed in this form or in this form. So here this J, which is known as the Colburn J factor, can be modified, right, by writing J is equal to H over G Cp multiplied by Prandtl number with the power of 2 by 3, right? So I will use this expression when we solve the design problem for the compact heat exchanger. So there are various techniques that has been used for the heat transfer enhancement, and which has been classified or segregated into two categories. The first one is the active techniques that requires the external power to the surface, such as surface vibration, acoustic or electric field, or the application of the electric field. So this requires the external power, and this is very costly process. The second technique is known as the passive technique, and which use the specific surface geometries with the surface augmentation, and which is the case generally applied in the design of compact heat exchanger. So the second point is In this slide I'm just trying to explain that you can just enhance the heat transfer coefficient either two techniques. The first technique, that is known as the active technique, and which requires the external power. So the external power is not always available, right? So the second technique is you just apply or modify the external surfaces just to enhance the heat transfer coefficient, right? So the heat transfer coefficient of an enhanced surface, which is given by the Colburn modulus J, and the friction factor of the surface F, and usually presented as a function of the Reynolds number, and I have already said that the J factor, which is Colburn J factor, is equal to the Stanton number, which we have just modified in this form, the heat transfer coefficient divided by the mass velocity and multiplied by the heat capacity into the Prandtl number with the power of 2/3. So this is the most important expression that can be used for the determination of the heat transfer coefficient. So I will show you how to use this expression, that, right? So ultimate objective is to determine the heat transfer coefficient, right, for the particular geometry, right? So for this we have different graphical representations that has been developed by performing different experiments, and from those graphical representation we will just get the value of J and other parameters like the mass velocity and the heat capacity, right? We will just develop or calculate the heat transfer coefficient. I will show you in the upcoming slide. So the friction factor of an enhanced surface in a single phase flow is higher than the smooth surface when operated at the same Reynolds number, right? So consider that the friction factor is relatively higher for the heat exchanger which has the extended surfaces rather than the heat exchanger which has no external surfaces or no extended surfaces, right? So therefore the enhanced surfaces would be allowed to operate at the higher pressure drop. What does it mean? It means that if we have a bare tube, right, if the fluid is moving on the outer side of the pipe which has the plain or the bare tube, it will have the less pressure drop. If we have the external surfaces or the fins on the outer side of the tube, it will have the high friction factor and it will have the high pressure drop, right? So the most common compact heat exchangers are the plate fin and the tube fin heat exchangers. I have already shown you the diagrams, and adding fins or external surfaces increases the heat transfer surface area of these types of the heat exchangers. This is very common point to understand. Due to the small passages, if we install the external surfaces on a particular area, so it will reduce the passages for the flow. So due to the small passages, dimensions, passage to passage, non-uniformities and geometrical variations, accurate characterization of the heat transfer surface is very difficult for the compact heat exchanger. So the most important point is due to the ever decreasing flow passages, because if we install the external surfaces on a particular heat exchanger, so the flow passages will be decreasing. So because of the increased friction, increased hindrance because of the external fins, and everlasting compactness. As you can know that if we install the fins, the flow will have the hindrance and the compactness of the surface will increase. Some of the assumptions which are applicable to the normal heat exchanger might not be valid for the compact heat exchanger, especially for the micro heat exchanger, which we have to assume we have to take the different assumptions while designing the micro or the compact heat exchanger. So it has wider applications in many fields. I have already explained that it has applications in the space industry and the refrigeration industry and the air conditioning industry as well. So let's talk about the heat transfer in the compact heat exchangers. So the compact heat exchangers are available in a variety of configurations of the heat transfer matrix. So the heat transfer and the pressure drop characteristics of the various compact heat transfer compact heat exchanger configurations for use are determined experimentally, and it has been represented by different graphical representation for the compact heat exchanger Coleman factor and the friction factor in terms of the Reynolds number. Let me just show you various graphs. So this is a graph for the heat transfer and the friction factor for a circular tube with the continuous fin heat exchanger, right? So this is actually the graphical representation. So these are the tubes, right? And these are the tubes, and this is the continuous fins, right? So this is the sideways look, right? And the different parameters such as the outer diameter of the tube and the fin thickness and the hydraulic diameter and the free flow area over frontal area, which is represented by sigma, and the heat transfer area over the total area or is represented by here, which is 587 meter square per meter cube. And there are different parameters which are given here for the compact heat exchanger, in which the geometry or the configuration is also mentioned that it is a circular tube continuous fin heat exchanger. So what you have to do is you will be given with the certain geometry, right? So for the exams point of view, you need to bring these graphs. So these are 4 or 5 graphs maximum. So you need to bring these graphs, right, as a supporting material. You will be given with the certain geometry, and you have to identify the geometry type after reading the question statement, and you have to look the different graphs, right? So if I mentioned in the question paper that the circular tube continuous fin heat exchanger, that means you will be using this graph, right? From the given parameters in the question statement, you have to determine first the Reynolds number, right? From the Reynolds number, you have to determine 2 different parameters from this graph. The one is known as the Coleman factor, right, which is given over here in this range, right? And you can determine from this graph, right? For example, the Reynolds number is 2 into 10 raised to the power minus 3. So this point is the Reynolds number. So first you need to determine the Coleman factor. What you have to do is you have to draw the straight line or the vertical line that will touch over here, and then you will draw the horizontal line. So 0.008 will be the Coleman factor or the J factor. From the J factor, you will have to determine further the heat transfer coefficient. And the second thing is, at the same Reynolds number, you have to determine the friction factor, right, which is in between this 0.020 or 0.023, which will be approximately 0.026, right? So you have to determine these 2 values from this graph. And similarly, there is a next graph which is for the different geometry, right? So this graph is for different geometry, and this graph is for different geometry, as it is mentioned over here, the heat transfer and the friction factor for the flow across circular fin tube matrix. The previous one was for the continuous fin, right? So this is the graph for the circular fins. As you can see that these are the tubes, and it has the circular fins, and every parameter is given over here, and as you can see at the bottom of this graph. So what you have to do is you have to follow the same procedure. You have to calculate the Reynolds number first, and then from the Reynolds number, and you have to determine the Coleman factor J and the friction factor for a particular given geometry that has been given in the question statement. This is another graph that the heat transfer and the friction factor for the flow across fin tube matrix. So this has a very different configuration as compared to the previous one. So as you can see that the different tubes are arranged at certain distance, right? So here the tubes are arranged in a compact manner, and here the tubes are arranged at a particular distance. So every geometry has has a particular graph that has been developed experimentally, and you need to use these graphs for the determination of the Coleman factor J and this is the Coleman factor J, and the formula has already been explained in one of the previous slide, that it is equal to this Stanton number, which is the ratio of the heat transfer coefficient, mass, velocity multiplied by the heat capacity, and the parental number to the power 2/3. So from this Coleman factor J factor, you have to determine the heat transfer coefficient, and you have to use the friction factor as well. I will also explain how to use this graph for a particular design parameter for the compact heat exchanger when I will explain the design problem in the upcoming slide. Note that there are three dimensionless groups governing these correlations, which are Stanton number and Prandtl number and the Reynolds number. And I have already explained all these three dimensionless number, where G is the mass velocity or the mass flux, which is the product of density, and the U max, which can also be represented as the ratio of the mass flow rate, total mass flow rate, divided by the A min, which is the minimum free flow cross sectional area. Let me just show you a few other high quality graphs. This is one of the same graph that I have already shown you in one of the previous slides. So instead of using the previous graphs, you can use this graph for the exam purpose, right? So all of these graphs becomes 5 to 6 graphs, and you have to bring all these 5 to 6 graphs, and you will have to use one of the graph for the design problem for the compact heat exchanger. So this is a particular graph for the heat transfer and the friction factor for the flow across the circular tube continuous plate fin heat exchanger, and similarly this is a graph for the heat transfer and the friction factor for the flow across the flat tubes, right? These are the flat tubes and the continuous plate fins heat exchanger, and similarly other parameters which you have to use for the design problem always mentioned on the graph. So these are constant, and you have to use as it is when you use or when you solve the design problem for the compact heat exchanger. And this is again the similar graph with the high quality, and you can use this graph for the design of the compact heat exchanger. And this is the graph for the circular tubes and the circular fins heat exchanger. The pressure drop for the plate fin heat exchangers, let's have a look on the few points that what kinds of the pressure drop that we have to face when we design the compact heat exchanger. The first point is, as the fluid enters the passages, it is subjected to the pressure losses owing to the sudden contraction resulting from a sudden change in the area. So there might be sudden contraction or there might be sudden expansion. So these effects are known as the entrance effect and the exit effect. So there will always be the pressure change and the pressure loss. So we have to incorporate that pressure loss when we design the compact heat exchanger. So as the fluid passes through the heat exchanger, so the core of the heat exchanger, so there might be the loss of pressure because of the friction. So we have to incorporate the friction factor or the pressure loss due to the friction. That is the second point. The first is because of the contraction of the fluid in the heat exchanger, and that is called the entrance effect. Second is due to the friction, and we have to incorporate the frictional effect. And third is depending upon whether the heating and the cooling basically occurring in a compact heat exchanger, the pressure change results from the flow acceleration or deceleration. So we have to incorporate the flow acceleration or the flow deceleration effect on the pressure drop. And the last point is, as the fluid exits the compact heat exchanger matrix, then there will be the pressure loss which will be associated with the sudden change in the area and the sudden expansion or the sudden exit or the sudden enlargement of the area of the flow. So that's why we have to incorporate this effect as well. So here is the whole equation which explains the different kinds of effects on the pressure losses. So delta P is the pressure loss, which is due to, the first one is the entrance effect, the sudden contraction, because the second is the flow acceleration, third is because of the friction, and the fourth is because of the sudden enlargement or the exit effect from the heat exchanger. So the total pressure drop for the flow of a fluid across the heat exchanger matrix is given by this K's and London by this equation. This is the final expression, right? So this is the first parameter or the first term, which is in the first parenthesis in this one. This is the effect which shows the pressure drop because of the contraction, and this is the effect which shows the pressure drop effect because of the expansion or due to at the exit point of the heat exchanger, and this is because of the friction, and this effect is due to the acceleration or the deceleration. So here the one important terminology that is known as the sigma, which is the ratio of the minimum free flow area divided by the frontal area. So here another ratio is given, A actual area over A minimum area, which is the total heat transfer area divided by the minimum flow area. And the next important terminology, which is known as G, which is simply known as the mass flux and the mass velocity, which can be expressed as the multiplication of the density multiplied by the velocity of the fluid divided by the sigma. So here different terminologies are also available, that is Kc and Ke, that are the flow contraction and the expansion coefficients, and the densities at the inlet and the exit point is represented by Pi, rho I and the rho naught. So the mean density can be determined by this formula. So there is one important point, that if we are using the fin tube banks, so the contraction and the expansion effects are negligible. So we can set the contraction coefficient or the expansion coefficient is equal to 0. So if we put contraction and the expansion coefficient is equal to 0, so this above expression, this is the expression which will reduce to only this expression, because the pressure drop, the contraction or the expansion terminologies will be reduced to 0 if we use the fin tube banks in which the flow would be normal to the fin tubes bank. So we will have the pressure drop formula, this one, right? So this is all about the introduction, basic terminologies, and the theoretical part, and the correlations and the pressure drop calculations about the compact heat exchanger with different geometrical configurations. So here is the design problem for the calculation of different design parameters for the compact heat exchangers. So let me just read the question statement, that air at 1 atm pressure and at the temperature of 400 Kelvin with a velocity of 10 meters per second flows across the compact heat exchanger matrix, having a length of 0.6 meter and having the following configuration. So this is the configuration which is given in one of the previous graphs, and this is the associated information. What you have to do is you have to determine the heat transfer coefficient, the first one. The second one is the ratio of the frictional pressure drop to the inlet pressure for the flow of the air across the heat exchanger. So what data that you will have in order to get the final values of the heat transfer coefficient and the pressure ratio of the frictional pressure drop to the inlet pressure. So the tube fin, circular tube, continuous plate fin is the configuration, and it is given in the question statement that the pressure is 1 atm, which is translated as 1.01333 into 10 raised to the power 5 Pascal, and the temperature is also given, that is 400 Kelvin, and the velocity of the air which is passing through the compact heat exchanger is 10 meter per second, and the length is 0.6 meter. So from this configuration which is mentioned over here, right, so the associated information which is given over here, you have to this one, that the minimum free flow area divided by the frontal area, which is represented by sigma, and it is 0.0534, and it is given over here, right, and the hydraulic diameter, which is the 0.3633 centimeter, which we have mentioned over here. What you have to determine is you have to determine the heat transfer coefficient, and the frictional pressure drop. So we have already studied the 4 different kinds of pressure drops that we encountered in the compact heat exchanger design, but here we just have to determine the frictional pressure drop, and ultimately we have to determine the ratio of the frictional pressure drop to the inlet pressure drop, and we will see that how much pressure is dropping because of this velocity of the air in the compact heat exchanger. So based on the given information, that is the temperature, we can have the different other parameters for the air, that is the density and the heat capacity and the viscosity and the Prandtl number. From this given information, we can determine the mass flux or the mass velocity, which is equal to, but after just putting the values over here, it will be 16.53 kilogram per meter square per second. And the second thing is, you have to determine the Reynolds number after getting the value of the mass velocity or the mass flux. So you have to determine the Reynolds number. The Reynolds number value is 2627. It can be translated as 2.6 into 10 raised to the power minus 3. So from this Reynolds number value, you have to determine the J factor and the value of F. Let me just show you in one of the next slide. So this is the graph, and with the given geometry, what you have to do is, the given Reynolds number value is 2.6 into 10 raised to the power minus 3. So this is the initial point of the Reynolds number that you have just calculated in one of the previous slides. So what you will do is, you will draw the vertical line right at this Reynolds number that will touch both the lines. This is the line for the J factor, Kolban factor, and this is the line for the friction factor. So again, you will draw the first horizontal line that will intersect this J factor, and you will get the value over here, which is the J factor, the Kolban J factor, and the second horizontal line you will draw over here, you will get the friction factor over here. And after getting the values of J, right, so which is 0.0071, and the friction factor is 0.025. So we know that the Kolban J factor is equal to Stanton number multiplied by the Prandtl number raised to the power 2 by 3, and if we open this one, it will be equal to the heat transfer coefficient divided by the mass flux Cp Prandtl number to the power 2 by 3, and it is equal to the Kolban factor J factor. So we have this value, we have overall this expression. From this expression, we'll just keep H, that is the heat transfer coefficient, on this side, and we'll take all other parameters like G, Cp and Prandtl number to the power 2 by 3. We'll take these parameters on the right hand side, and we will try to put the values of Prandtl number, which is mentioned over here, that is 0.689, and G value and the Cp value, and after putting the value, we will get the heat transfer coefficient. Let me just show you in one of the next slides. So here, so after putting all the values of G, Cp and the Prandtl number, you will get the value of the heat transfer coefficient, which is equal to 152.6 watt per meter square per Kelvin, right? So this is the part A that you have to determine, right? And the second step is, you have to determine the frictional pressure drop. So you know that the pressure drop has 4 different kinds of pressure drops. In this question statement, you have been asked to calculate the pressure drop just because of the friction. So you will just keep the pressure drop terminology which is related to the friction, and you have all the parameters. You will just put the values over here, and ultimately you will get the value of the frictional pressure drop that will be equal to 2556.4 Pascal. And ultimately you will have to determine the ratio of the frictional pressure drop to the inlet pressure drop. So the frictional pressure drop is here 2556.4, and the inlet pressure is 1.01333 into 10 raised to the power 5, and after dividing it, multiply by 100, you will get the percentage that will be equal to 2.52%. This is the pressure drop because of the friction in this heat exchanger. With this is the end of the lecture.